Okay, so far we have seen the sorting algorithm, which are basically comparison based sort. So that means we have we compare two elements to know their ordering. So basically we compare the elements to get the ordering. So those are basically comparison based sort. So comparison based sort. Sorting algorithm. So like we have seen insertion sort, then we have seen the merge sort, then we have seen the quick sort, and a version of randomized quick sort. And also we have seen heap sort. So all these sorting algorithm we have seen are basically comparison based sort. So that means we compare two elements to get their relative ordering. So these are comparing the elements, comparing the input elements. So these are comparison based sort. So what are the time complexity for this sorting algorithm? So the question is how fast we can sort. So that is our topic today. I mean, so how fast we can sort. Okay. So far these are the sorting algorithm we have discussed. So let us have a time comparison table for this sorting algorithm. So let us have best case, average case, and the worst case time complexity of this. Okay, so we talk about, we have seen insertion sort. Okay, insertion sort best case we know it is a order of n. That means when it is when the array is already sorted, and that will give us the best case. And average case we have seen is also order of n square, and the worst case is also order of n square. And then we talk about merge sort. Merge sort we know all the cases it is basically order of n log n, because it does not matter whether a input is sorted, reverse sorted. We go to the middle, we just partition it, we just go to the middle, we divide into two sub array, we sort this sub array, then we call a merge subroutine. Then it is a all the cases is in order of n log n, and it is not a in place sort, because to call the merge subroutine we need to have a extra array. So then we discuss the quick sort, and the best case we have seen it is n log n. Okay, when we choose the pivot is maximum or minimum always. And the average case, this average case analysis we did for randomized version of the quick sort, which is the expected runtime. This is the randomized version of the quick sort, randomized quick sort. And then the worst case we know order of n square for quick sort, because worst case it is always we choose the pivot is best case we do not choose the pivot is minimum or maximum. For the worst case we always choose the pivot is to be maximum or minimum, then it will be partition is 0 is to n minus 1 always. Okay. And then we talk about the heap sort in the last class, which is also all the cases it is order of n log n. So basically we make use of the data structure heap. So now the question is, in the we are basically concerned about worst case. So our question is how fast we can sort in the worst case. because worst case is the most usual case one should go for, because it's give us a guarantee. So, the question is how fast we can sort. So far we have seen this is the best way, the order of n log n, which we are achieving by merge sort or in the heap sort in the worst case, and merge sort is not a in place sort, but heap sort is a in place sort. Everything we are doing in that array. Okay, we do not need any extra storage for heap sort. So now the question is this the faster way, or we can reduce the worst case time complexity further. So the question is, can you sort less than order of n log n time in the worst case. So that is the question in the worst case. So the question is this the best one in the worst case scenario, or we can have some better algorithm which will give us the worst case time complexity better than order of n log n. Order better than order of n log n means it could be linear, it could be log n, it could be n log n, something like that. So it should be time complexity should be lesser than less than this. So that is the question. So the answer is, if we are using the comparison based sort, so that means if we are comparing two elements to get their relative ordering, then the answer is no. So there is no comparison based sort which can give us the worst case time complexity lesser than this. So for any comparison based sort, if we consider, that will give us the worst case, I mean this is the lowest one. We cannot reduce this time further. So that we have to convince by the help of what is called decision tree. So we will take the help of decision tree model to convince this answer that if we use some comparison based sort, any comparison based sorting algorithm, we cannot do better than n log n in the worst case. So let us convince this with the help of a decision tree. So what is a decision tree? So basically decision tree example, suppose we have given 3 numbers to sort A1, A2, A3. Okay. 3 numbers are given A1, A2, A3 and we need to sort. So what we do, we will form a tree, decision tree. So for that, for making this tree, we assume this number are distinct, all are distinct. A1, they are distinct number. These are input and we need to sort. So we have 3 distinct numbers. Okay. Okay, now how to form a decision tree? So first we compare A1 with A2. So 1 is to 2. This we write in this way. So we are comparing A1 and A2. So A1 is a number, A2 is a number, and these two are distinct. So if we compare two numbers which are distinct, then what are the possibilities? We have only 2 possibilities, because we are not taking they may be equal. So equality possibilities is gone. So we have 2 possibilities, either A1 is less than A2 or A1 is greater than A2. So if A1 is less than A2, we will go to some branch, left branch, and if A1 is greater than A2, we will go to right branch, and we will do the subsequent comparison again. So this branch will go if A1 is less than A2, and this branch will go if A1 is greater than A2. There is only 2 options because these are distinct. Okay, now if we follow this branch, again we compare A2 and A3. So again if we compare A2, A3, so there are 2 possibilities, either A2 is less than A3 or A2 is greater than A3. So again we have 2 possibilities. So this way A2 is, so we will go for further comparison, if A2 is, this is the branch for to follow if A2 is less than A3, and this is the branch if A2 is greater than A3. Okay. Now, if we reach to this branch, A1 is less than A2, A2 is less than A3. So, this will reach to a decision. What is the decision? This is telling us A1 is less than A2, less than A3. This is the decision. So, this we denote by 1, 2, 3. Okay. Suppose we have an example such that A1 is less than A2, then we will follow this branch, again we compare 2, 3, A2 is less than A3, then this is the branch we follow and this will reach a decision. So, these are all, this is the leaf node. Now, here if we go for this branch, then we have to compare again A3 with A1 with A3 to reach to a decision. So, if we compare two number again, so we have two possibilities, A1 is less than A3 or A1 is greater than A3. So, if A1 is less than A3, so we know that A1 is less than A2 and A2 is greater than A3, and here A3 is greater than A1. So, this is giving us the decision like 1, 3, 2. That means A1 is less than A3, less than A2. Okay, because A1 is less than A3 coming from here, and then A2 is greater than A3, and then again A1 is greater than A3. So, if we follow this branch, it is reaching us to a decision that A1 is less than A3, less than A2. And similarly, if we follow this branch, then it will reach to a decision 3, 1, 2. That means A3 is less than A1, less than A2. Okay. Now, come here. So, if A1 is greater than A2, then we have to do further comparison. Okay. So, we compare A1 with A3. So, if A1 is less than A3 and we know that A1 is greater than A2. So, this will reach to a decision 2, 1, 3. So, that means A2 is less than A1, less than A3. Now, if we have to follow this branch, so then we have to compare again A2 and A3. Okay. So, this will reach us to a, so this is basically, this should come down here. So, this is basically 2 A2 A3. So, this is giving us two decision. So, if A2 is less than A3, so this is basically A1 is greater than A3 and this is A1 is less than A3. Okay. So, this is reaching to a decision 2, 3, 1 and this is reaching. So, this is A2 is greater than A3. This is reaching to a decision 3, 2, 1. So, this is basically A3 is less than A2, less than A1 and this is A2 is less than A3, less than A1. Okay. So, this is called decision tree. Now, we can take an example. Suppose we take say 9, 4, 6. Suppose this is our A1, this is A2, this is A3. Okay, A1 is, so A2 is 4, A3 is 6. Okay. Okay, so we want to follow this model. So, now we start with here, we compare. So, this is the model we have, this tree we have, this is the decision tree. Now, first we compare A1 with A2. So, A1 is 9, A2 is 4. Now, 9 is greater than 4. So, we must follow this path. Okay. And then because we have to follow this path because 9 is greater than 4, then we have to again do the subsequent comparison to reach to a decision. These all leaf nodes are basically giving us the decision. So, they are basically permutations. So, leaves are basically all possible permutations. So, there are 3 nodes. So, there are factorial 3 permutation. So, factorial 3 is 6. So, 6 permutation. Okay. So, here 9 is greater than 6. So, we follow this path. Then again we, after reaching here, we have to compare A1, A3. So A1 is 9, A3 is 6. We compare 9 and 6. So if, so 9 is greater than 6. So again we follow this path. Okay. Now again we have to compare A2, A3. A2 is 4, A3 is 6. Now 4 is less than 6. So we follow this path and we reach to a decision. What is the decision? That A2 is less than A3 is less than A1. So what is A2? A2 is basically 4, 4 is less than, A3 is 6 and less than 9, which is correct basically. So this is sorted. So every path is, if we, so for a given input basically we are following a path to reach to a decision. So to reach to a, to get a sorted array, so this is our input, we need to sort it. So we start with the root and we compare two elements and then based on the comparison either these are distinct element. So basically what we have say nodes are basically I is to j. So basically here we are comparing ai and aj and these are distinct nodes, distinct element. So if we compare two elements, then ai is either less than aj or ai is greater than aj. So if ai is less than aj, then we will go to the this subtree and we do the subsequent comparison until we reach to a decision. And then if ai is greater than aj, we will go to this subtree, right subtree, until it and we keep on comparing again until it reach to a decision, until it reach to a leaf node, and every leaf contain a permutation, and that is the ordering between the elements. Okay. So any comparison based sorting algorithm we have seen is basically execution of any comparison based sorting algorithm we have seen basically execution of this decision tree. So we basically every comparison based sort, if you compare, if you think like insertion sort what we are doing, we are comparing two elements and then we are taking a decision. So basically same thing. So any comparison based sort basically we are comparing between the elements and we are going and further comparing, again we are further comparing and finally we are reaching to a decision, finally we are reaching to a permutation which is giving us the ordering of that element. So this is basically the decision tree model, and which is basically the any comparison based sort, execution of any comparison based sort is basically the path, execution of the path of the decision tree from root to the leaves. So here any node is basically of this form I is to j. So this is basically comparing the ai with aj. Now if ai is less than aj, we go for this path and we do subsequent comparison, and if ai is greater than aj, we go for this path, we do the subsequent comparison. So this is the model of decision tree, and any comparison based sort is basically fit under this model. Okay. So and what are the leaves? So leaves are basically each leaves so each leaves contain a permutation say pi 1, pi 2, pi n, that indicates that they are in that order. That indicates that a pi 1 is less than a pi 2 less than a pi n. Okay. So that means they are in the order. So we reach to a decision. So this is a decision. This is a decision. Depending on the input, we reach to that particular I mean one of this path, one of this leaf, and that is a decision. So, each leaf contain a decision. So, basically any execution of any comparison sort is basically we just execute the route to the leaf. Okay. So, basically the runtime, so runtime depend on the length of the path. Now, here if the input is say 946, then we follow this path. Okay. Now, if the input is say instead of 946, if the input is say 9 6 and then say 10. Okay. Then what we do? So, we just this is our A1, A2, A3. If the input is this, then what is the path? The path is basically, let us erase this earlier one. So, path is basically we compare A1 with A2. So, we follow this path, then again we compare A1 and A3, A1 is 9, A3 is 6. So, we follow this path. So, we reach to a decision. What is the decision? A2 is less than A2 is 6, which is less than A1 and which is less than 8, which is correct, and length of this path is small. So, depending on the input, I mean the time complexity will be the length of the path of a decision tree. So, let us write this. Okay. So, the runtime of this decision tree model of the algorithm is equal to the length of the path taking. Okay. For this input we go to the less length, but then what is the worst case runtime? Worst case runtime will be the height of this tree, because that is the worst case. Worst case means maximum path we follow, okay, and that is the height of the tree. In the worst case means we have to follow the route to the maximum length path, and that is the height of a tree. So, the worst case runtime is basically height of the tree, okay, and this is denoted by h, and we prove that height of this tree is n log n, and that will give us the answer that in the worst case any comparison based sort, we cannot have a comparison based sort which can be better than n log n. So, let us talk about how the worst case, how the height of this decision tree is n log n. Okay. So, this we prove by a theorem. So, this theorem is telling any decision tree that can sort n element must have height. So, height must be bounded by n log n, lower bound. So, height must be greater than or equal to n log n. So, this we have to prove. Okay. So, to prove that, suppose we have n elements. So, in the example we are having 3 elements and we form the tree. Now, suppose we have n element and we form the tree. So, what is the number of leaves? So, number of leaves is basically all possible permutation. Basically, they are the decision, we do not know which input it will come. So, the number of, so decision will be, so we should have a decision for all type of inputs. So, that means, and each leaf is basically the decision. So, for a given input we execute the path and we reach to a decision. So, number of leaps must be factorial n, and this is the all possible permutation. I mean, this is the permutation of n inputs. So, this is the number of leaps. Okay. Now, this is a binary tree. So, that means we have each node have 2 nodes. So, if the height is h, let h be the height of the tree. Okay. Then 2 to the power h must be greater than equal to factorial n, because then the number of leaps must be 2 to the power h. Why? Because so height is h. So, if we have a complete binary tree like this, okay, then this is the height means maximum depth if the height is h. So, at this level what is the number of nodes? 2, this level 2 square. So, if the height is h, so if he is in a complete binary tree, then the number of leaps will be 2 to the power h, but it is not a complete binary tree. There are some leaps, some branches are ending fast. So, that means if it could be complete, then it is 2 to the power h. So, that means the number of leaps must be less than 2 to the power h. So, from here we know the number of leaps is factorial n, it is basically 2 to the power h. So, now from here we can just write h is basically greater than equal to log of factorial n. Now, we will use a formula which is the Stallings formula. So, let us okay. So, what we have? We have h is greater than equal to log of factorial n. Now, factorial n can be approximated by n by e to the power n, and this is called Stallings formula. This formula is Stallings formula. So, if we use here this, so h is greater than equal to log of n by e to the power n. So, this is basically h is greater than equal to n log n minus n log e. Okay. Now, this is a lower order term, we can ignore this. So, this is basically height is basically bounded by n log n. So, this is basically height is omega n log n. So, the height of a decision tree cannot be less than n log n, it is a lower bound by n log n. So, omega l big omega of n log n. So, that means once worst case runtime of any comparison based sort is bounded by lower bounded by n log n. So, we cannot sort n element faster than n log n if we are using comparison based sorting algorithm. Okay. And this we have seen by the help of decision tree. So, next class we will talk about linear time sorting algorithm, but those are not comparison based sort. We are not comparing the between the elements, we are just seeing value of the element and we are putting into the bucket. So, those are basically bucket sort, we will discuss in the next class. Thank you.